Hi, my name is Ammon Cadigan. I'm a graduate student at the University of Arizona, and for my research I studied a method of measuring the amount of water that flows through a river using drones. And I wrote a paper about this. It's pretty long and full of lots of science talk, jargon, and equations. You can read it if you like, or you can watch this video and get a brief introduction about what I did. So why use drones to measure the amount of water that flows through a river? And to answer that question, it's first important to understand why someone will want to know how much water flows through a river in the first place. And as you may or may not know, floods are the most common natural disaster in the world. And a key component in mitigating the damage to structures and human life by flooding is to know how much water flows through a river during a flood. In hydrology and hydraulics, we call the amount of water that flows through a river discharge. So a key component in knowing the discharge of a river is knowing how fast the water is moving through the channel. And so you might say, okay, well, it's pretty easy. You just measure the speed of the water. Unfortunately, measuring the speed of the water is not that easy. So it turns out there's an organization that regularly makes these flow measurements on rivers, and it's called the United States Geological Survey. So you may or may not have heard of the United States Geological Survey when you hear about earthquakes and volcanoes, but they actually do a lot of water stuff around the country, and you, the American people, pay for it. That's pretty cool, right? So anyways, the US Geological Survey has trained professional scientists that go out across the country and make these discharge measurements on a regular basis. And most times it's pretty easy and pretty smooth, but when there's a flood event, it can get kind of sketchy, especially when cable cars are involved. But not only is it dangerous and difficult, it's also often not super accurate. And that's because traditional methods of measuring flow during a flood event don't work super well when there's a lot of junk in the water, like dirt and trees and, I don't know, houses, cows. Anyways, there's a lot of stuff in a river during a flood event that makes it so these methods don't work as well. So not only is it dangerous, but it's also not super accurate. So this is where drones come in. In recent years, drones have become increasingly affordable, stable, and reliable. For example, this little guy, this Parrot Anafi, can record 4K video at 30 frames per second, has built-in stabilization, and it's not that expensive, relatively speaking. So at this point you might be wondering, how exactly do you measure flow using a drone? Now you might already know, but when a camera records video, it's basically a bunch of pictures that are shot in rapid succession. So for example, my drone shoots at 30 frames per second. So if I shoot a 20-second video at 30 frames per second, that means that the drone recorded 600 pictures. These pictures that are captured from the drone can be used to track features on the water surface using a method called large-scale particle image velocimetry. Now, I'll show you how it's done, or an example how this is done, with this simple paper here. So I've created this paper model to demonstrate what things look like from the viewpoint of the drone and how that's used for this analysis. So this view that you're looking at right now is what the drone sees when it's flying directly over the water surface. The drone can see both the water with all the stuff floating on the water surface and then the two banks. And then on the right, you can also see that there are 2 points which will serve as calibration points. As the water flows through the field of view, the camera records the moving particles. Since we know the frame rate of the camera and the distance between the two calibration points, we can find the velocity of each one of these particles and use it to create a two-dimensional velocity distribution. Okay, so we recorded the video on paper to give a simple example of what's going on, and this is what the video looks like here. So the first step is to split this video into individual frames, and that's done using a software called River, which is this right here. I'll put a link to where you can download it in the description to this video. So the first step is you go to File, Extract Images from a Movie. You find the location of your file here. So this video is a 10-second video that's shot at 30 frames per second. So that means if we extract every frame, we will extract 300 frames in total. So go ahead and click extract. And what it does is it puts out this folder here where it's got all the pictures that have been split up from the original video. If we just open one of them, this is what it looks like. You can click through them and you can see the movement of the different particles in the river. Now, if you have the PIVlab software downloaded on your computer, you can enter into PIVlab from River by going to File, PIVlab, PIVlab GUI. Awesome. So now that PIVlab GUI is open, we can perform the background subtraction by first going to Image Settings, Image Pre-Processing, and then you go to Background Subtraction GUI. So we're going to go ahead and select the images that were output from River. Okay, so got all the images here, all 300 of them. I'm going to select them all, click Open. I'm going to make sure it goes 1 to 2, 2 to 3, and 3 to 4. Okay, now I'm going to click Subtract Background and Save Images. It's going to ask me to put a folder, so I'm just going to create a new folder here and do test subtracted. Select folder. Okay, great. Once it reaches 100%, you can go ahead and close out of here. And just to show you what the difference is, when we go to subtracted here, it basically just highlights the particles that are moving. That's a little hard to see here, but the software is going to be able to pick it up really well. So now that we have the background subtracted from all the images, and we've got PIVlab GUI open, we can go ahead and perform the actual PIV analysis. The first step is you go to File, New Session, and then when you do that, it's going to have a pop-out box that pops open, and you're going to be able to select your images. So the first thing is you go to Sequencing Style as 1 to 2, 2 to 3, 3 to 4, and then click the dots here to navigate to the folder that your subtracted pictures are saved in. Click select that folder, and you can select all the pictures that you want to bring in, and then click Add, and then Import. So now you can see that we've got all the images here in the PIVlab GUI workspace. We have the calibration on the side. So what I usually do first is I select the region of interest. But you go to Image Settings, Exclusions, Region of Interest, Mask. So to select the region of interest, it's just a box like so. Okay, and this region of interest is where your velocity vectors are going to be calculated from the movement of the particles. So I put the region of interest over the water surface, and I also try to make it pretty long in the streamwise direction. I'll also calibrate it. You don't need to do this before. You can also do it after you run the PIV analysis, but I just find it's good practice to do it before. We're going to just select a reference distance here, and it gives you this black pointer thing that you can choose your 2 calibration points. And I know that's 10 meters here, so I'm going to say that is 10,000 millimeters. In the time step, you actually get from your original image extraction folder. This is the results from River. It will give you the time step here, which is 33.333 milliseconds. So I'm just going to copy that and paste it here. There you go. I'm going ahead and apply the calibration. It's all set up and ready to go. Go to Analysis, and the first thing you're going to have to put in is the interrogation area, which I set to 128, and then the step is 64. So you want it to be 50%. Then the next pass is going to be 64, and then I always do 32. So you can analyze current frame just to see what things look like. Okay, so it looks pretty good. That's what I would expect the velocity vectors to look like. So then what you would do is you go to POV slide analysis, and then go to Analyze, and then you click Analyze All Frames. PIVlab gives you an idea of how long it's going to take. For these 300 frames, it's saying that it's going to take 7 minutes and 46 seconds. All right, so once PIVlab has finished, you can go through and you can see each one of the calculated velocity fields from each individual frame by just going through this little box through here. What I usually do is I go to post-processing, vector validation, and then I select velocity limits. And basically what this is here is that it gives you all the velocity vectors that occur in your data set, and you can filter out ones that you know are erroneous. So I'm going to refine velocity limits here. Okay, so by selecting this box here, I will be choosing what velocity vectors are erroneous. And I know that from this spread here, it looks like all of them are concentrated within this area, so it looks to me like I should probably select something like this, like that. And then you click apply to all frames. Okay, now you can see that once the velocity limits had been applied to all frames, there are now these orange arrows which show that they have been removed from the data set. So you can, if we scroll through, you can see those vectors which were outside the box that we specified have been removed. If you want, you can also calculate a average velocity field. If you go to plot, derive parameters, modify data, and then you can calculate mean. And now this shows you your mean velocity field. Now in a normal river, you would expect to see smaller vectors near the walls and the largest vectors near the middle, because that's how flow goes. It generally follows like a parabolic shape. But this is just a simple example where I just moved all the flow at once to kind of show you how to do stuff in PIVlab. So, you know, it seems pretty accurate that all these arrows are the same length across. So if you want to export that into a MATLAB file where you can, you know, mess around with the vectors there and calculate turbulence dissipation rate, you would go to File, Save, Mat File. You can also extract parameters from a polyline. Like let's say you want to find the distribution of velocity across the surface here. You can go to the polyline. I want to look at velocity magnitude. I'm going to draw from this point to this point. And then you click plot data. And you know, again, this is just from using markers and paper, so the velocity distribution doesn't look very good, but under normal circumstances, it followed a parabolic shape. So this example that I showed you here, you can see there's quite a bit of stuff on the water surface for the drone to pick up the movement. But a lot of times especially in man-made channels, there aren't a lot of particles or debris on the water surface for the camera to track. And that makes it so that the velocity distribution that you obtain via LSPIV isn't accurate. And for channels like that, I developed a seeding apparatus that would basically shoot out particles on the water surface. To do this, I bought a leaf blower and cut the hose right at the middle, added a T, and above the T I added a PVC valve that moderated the flow of the seed from the reservoir. And this type of seed that I used was rice cereal or Rice Krispies. And so just basically bought a whole bunch of Rice Krispies and put them into this seeding apparatus and tested it out. So as you can see from the video, it worked pretty well. That was just a test from my front yard in Tucson, but I got it to shoot around 50 feet. So for more narrow irrigation channels, that seemed to do the trick in order to get things to track. So I'll show you a before and after of what seeding looks like. Here's the Gila River without seed. Now you can see here that there are some particles which are already in the river, but really not enough for the camera to track so that it can create this great velocity distribution. So I use my leaf blower and distributed seed upstream. You can see it's starting to come into the field of view. And now you can see more, you can have a better idea of the velocity as it moves downstream. It also picks up these small eddies on the water surface, which is critical for estimating the turbulence dissipation rate, which I'll be talking about later. Okay, awesome. So we've walked through how you get a surface velocity distribution from the videos you record from the drone. Now, before we get too far, there's something important that you need to know about how discharge is calculated in hydrology and hydraulics. So just to give you the basic definition or equation of discharge, Q, which is equal to flow, is equal to velocity multiplied by area. Now this V is the depth average velocity, which is different from the surface velocity that's recorded from the drone. So I've got this figure here to show you what a velocity profile looks like. This is the bed, that's the water surface, and the velocity we measure at the water surface is different from what's underneath the water. To demonstrate this, I got this logarithmic velocity profile, and I'm going to draw these velocity vectors here. And as you can see, as you go further and further away from the bed of the river, more towards the water surface, velocity is getting higher and higher. So that means when we measure the velocity from the drone up here, which is equal to the V surface, it's very different from the velocity that we measure here, which is equal to the V average, and that's the depth average velocity. Now remember, this V average is the velocity that's used in that Q equals V times A equation. So in order to convert the surface velocity into depth average velocity, the following equation is used, where V average, the depth average velocity, is equal to V surface, the surface velocity, multiplied by the velocity index, often referred to as alpha. The velocity index is such an important part of the discharge measurement when you're using a drone. It basically decides how accurate the overall estimate is. So how do you find this magical velocity index value? Most times people just choose a velocity index based off prior knowledge of the study site. Some researchers have gone a little bit further in this qualitative method by saying that the velocity index is a function of channel depth and type. Specifically, these researchers here say that if you have a natural river which is under 2 meters deep, you should use a velocity index value of 0.8. If it's over 2 meters deep, then you should use a velocity index value of 0.9. They also say that any unnatural river, such as a concrete channel, should be assigned a velocity index of 0.9 regardless of the flow depth. So this method of choosing a velocity index based upon the channel type and depth works pretty well, but I wanted to see if there was a way that you could somehow calculate the velocity index. Turns out I'm not the first person to ask this question. There are some researchers who've been using a turbulence property called the turbulence dissipation rate to calculate flow properties such as the velocity index, most notably Johnson and Cowen and Jin and Liao. So you might be wondering what this turbulence dissipation rate is, and to be honest, I'm still trying to wrap my head around it myself. There are some researchers who spend their whole lives studying this turbulence thing, and they've got it figured out. So I use their works as a reference for me to understand what it was. From the Richardson's view of the energy cascade, turbulence can be modeled or thought of as a bunch of eddies of different sizes. These larger eddies are constantly breaking down into smaller eddies, which are breaking down to even smaller eddies, and so on. This rate that eddies break down from large eddies to small eddies is referred to as the turbulence dissipation rate. So to find the turbulence dissipation rate, I employed two different methods. The first method that I looked into was the one-dimensional velocity spectrum method, and the second method that I looked into was the large eddy PIV method. Now, I'm not going to get into the weeds of how each of these methods is done. If you want more information about that, you can read a bunch of papers. But just to give you a brief introduction, The one-dimensional velocity spectrum method uses a fast Fourier transform of velocity fluctuations in wave number space to find the turbulent dissipation rate. And the large eddy PIV method uses the subgrid scale stress and strain rate tensors to find the turbulence dissipation rate. So if that didn't make any sense to you, that's okay. It didn't make sense to me the first time, but I'll make sure to put some resources that you can read if you're looking for more information below. So like I said before, you probably don't understand super well what the turbulence dissipation rate is or how to calculate it. But the take-home message that I want to share with you, or that I found from my research, is that for me and the study sites that I looked at, the one-dimensional velocity spectrum method generally obtained better estimates of the turbulence dissipation rate compared to the large eddy PIV method. And I think this is probably because the large eddy PIV method is so dependent upon the resolution that's obtained from the video. And since you're flying a drone 30 to 50 feet up above the water, it's hard to get such high resolution video of these small eddies on the surface of the water. So it makes it so that large eddy PIV method isn't as accurate as the one-dimensional velocity spectrum method. For this reason, I use the one-dimensional velocity spectrum method to find the turbulence dissipation rate for all the studies, or for all the sites in this study. So now that we have the turbulence dissipation rate from the one-dimensional velocity spectrum method, we can use it in conjunction with the Manning's equation and the law of the wall to estimate the velocity index. And if you want to see more about how this is done and see the equations behind this, make sure to check out my thesis in section 5.1. Okay, so that's what I tried to do. Now I'm going to get into a little bit more of the results of this project and how things worked out. So to start off, I'm going to talk about the velocity index calculations from the turbulence dissipation rate method. So this figure here shows a typical distribution of the velocity index as calculated from the turbulence dissipation rate method. This is from the Androscoggin River up in Maine. The y-axis here is velocity index, the x-axis is distance from the left bank. The green line is the velocity index as calculated from the turbulence dissipation rate method. The purple line is calculated by dividing the depth average velocity from the ADCP or flow tracker by the surface velocity from the drone. So in other words, this purple line is the baseline measurement. That's what it should look like all across the width of the river. As you can see, the estimates of the velocity index from the turbulence dissipation rate are especially high near the riverbanks. And this isn't unique to the Androscoggin River. I plotted all the channels here in this figure here. Every channel is a different color of circle. Velocity index is on the y-axis. Normalized distance from the wall is on the x-axis, meaning that at 1, you're in the center of the river. 0 means you're on the banks of the river. And as you can tell from this figure, all the channels show higher velocity index values near the walls of the river. Having these high velocity index values near the banks of the river is a problem, because that means if I use the entire distribution of the velocity index across the entire width, I will be overestimating discharge, especially near the banks. So to verify if errors in turbulence dissipation rate were causing these high alpha estimates near the riverbanks, I calculated errors in turbulence dissipation rate estimates and plotted them against normalized distance to the wall. And you can see that in this figure here. We have normalized errors in the turbulence dissipation rate estimates. On the y-axis, on the x-axis is normalized distance from the wall. And as you can see, there is a general trend of decreasing errors in turbulence dissipation rate estimates as you move from the walls of the river to the middle of the river. There are a couple exceptions to this phenomenon, namely the Reservation Main Canal, which had these yellow circles, and the Gila River, which had these pink circles, which actually tend to increase towards the center of the river, and that's caused by wind and really shallow depths, which affect the measured turbulence. But this phenomenon of having the higher errors near the walls in the turbulence dissipation rate estimates can be explained by the isotropic nature of flow as you move away from the center of the river. And what I mean by isotropic nature is that when you're in the center of the river, flow has a preferential direction, meaning it's in the center, the water is mainly moving downstream. But as you move more towards the banks of the river, flow also moving against the current, it's moving in all different directions, meaning it's more isotropic. And because of the isotropic nature of flow near the walls, that equation that we use to estimate the turbulence dissipation rate is no longer valid, because it assumes that the distribution of the turbulence dissipation rate is linear with depth. So this method of estimating the turbulence dissipation rate doesn't work well when you are near the walls and secondary currents are dominating. So again, the issue here is that the velocity index values are way too high near the banks. And so to resolve this issue, I average the velocity index values in the center third of the channel and apply them to the entire width. So to show you what that means, I've got this figure here. On the y-axis we have the velocity index, on the x-axis we have distance from the left bank, and the pink line shows velocity index estimates from the turbulence dissipation rate method, and this blue box shows the center third of the channel. Basically what I did is I averaged the velocity index values in the center third of the channel and I applied them to the entire width, which is this yellow line. So to drive home the modification that I used, I originally had calculated each alpha value across the width of the channel and had used each alpha value, multiplied it by the corresponding surface velocity and corresponding area, summed them up to get the total discharge. The revised method that I use is I average the velocity indices in the center third of the channel and use that average velocity index, multiplied it by each surface velocity value and each area value across the width of the channel, summed them up to get discharge. So this is what the results look like for one channel when you try the two different methods. So again, the pink line is that turbulence dissipation rate method when you do not average the center third of the channel. The yellow line is when you do average the center third of the channel, and the green line is actual measured discharge values from the USGS. Again, I should mention that the discharge is on the y-axis here, x-axis is distance from the left bank. So as you can see with the pink line, when you do not average the velocity indices in the center third of the channel, you're getting really high values of discharge near the banks, which produce a very positive bias upon the results. But when you do average the center third velocity indices and apply the entire width of the channel, you're actually, the discharge estimates are very close to the measured discharge estimates across the entire width. So now I want to talk about the percent error of each one of these methods. Again, this pink box here shows the turbulence dissipation rate method when you do not average, and this yellow box here shows the turbulence dissipation rate method of estimating the velocity index when you do average in the center third, and the blue box here shows a more qualitative method of estimating alpha, or the velocity index across the channel, using the depth of flow and the channel type. So basically you're just choosing one velocity index value for your discharge estimates. So I've color coded these boxes here for red to show very positive percent errors and blue to show very negative percent errors. So if you have a more gold or yellow color, that means you have a percent error which is very close to zero, meaning it's accurate. So as you can see just right off the bat, the turbulence dissipation rate methods of estimating the velocity index generally overestimate discharge. So the method where you do not average the velocity indices across the center third of the channel produces a percent error on average of 66%. However, when you do average the velocity indices in the center third of the channel, the percent error drops from 66% to 42%. So that's a pretty good drop of 20% in error when you by averaging the center third of the velocity indices. However, when you compare that against the method proposed by Hauet et al. In 2018 of selecting a velocity index based upon the channel depth and type, the percent errors are much lower in magnitude of 20% compared to 42%. However, there are some other things to notice, like the rivers that had higher discharge values, such as the Agua Fria River, the Coachella Canal, and Androscoggin River, generally had lower percent errors, such as 15%, 9%, and 4%. So some key findings from the discharge calculation was that percent error in discharge estimates obtained from using the turbulence dissipation rate velocity indices decreases as discharge increases. So this figure here demonstrates that point. So we have percent error on the y-axis, discharge on the x-axis. This pink line is the turbulence dissipation rate method when you do not average the velocity indices in the center third. This blue line shows the turbulence dissipation rate method of estimating the velocity indices when you do average the center third of the estimates and apply them to the entire width. And as you can see, as discharge increases, percent error decreases. And so that's actually pretty good news, because that means that for these larger flood flows, this turbulence dissipation rate method will be more and more accurate as discharge increases. So to sum things up, I'm going to show you a couple of take-home messages. The first is that you can estimate discharge from a drone. The second is that the turbulence dissipation rate of estimating the velocity index works, especially for rivers where discharge is high. And the third is that discharge estimates using the turbulence dissipation rate velocity indices are less accurate on average than selecting a velocity index based upon depth and channel type. However, I have found that as discharge increases, the percent error in the turbulence dissipation rate method decreases. So I'd say there's still potential in this method, but if you're just looking for a simple one-off method to calculate discharge using your drone, I would recommend using the Hauet ETL method proposed in 2018, where you select a velocity index based upon channel type and depth. So that's it, everyone. Thanks for watching. If you want more information about any part of this project, you can check out my thesis. You can find it online at the University of Arizona. They have a database of all theses and dissertations. I'd also like to thank everyone who helped me with this project, specifically everyone at the United States Geological Survey, the University of Arizona, my advisor, Dr. Duan, and of course the Water Resource Research Center for providing funding for this work. So thanks for watching, and I hope you learned something. Thank you.